Okay, so I'll just wait for everyone to get, I think people are coming in now. If you could, you can use the chat to, the chat function to ask questions. If someone could just message just to say that they can hear okay, because I think there's a slight lag in the system. So we're going to cover 3 questions from the last 2 years' exam papers. We're going to do question 3 and 4 from last year's paper, and then question 2 from the year before that. Okay, so question 3, so just wait till everyone gets here. I think there might be a few more people coming. Okay, can everyone hear all right? So again, you can use the chat function to ask questions as we go through, but there's about a 20 or 30 second delay, so I might not get. Okay, can everyone hear all right? So I'm still quite new to the live stream thing. It's quite stressful actually. So there's 3 of you are here at the minute. Okay, so has everyone got the exam questions with them? So again, you can ask questions, but there's a slight delay. So we're going to do question 3 and 4 from last year. So question 3 was broadly about vector autoregressions. The first part asks you to verify whether the process is stationary or not. Then asks you to put the process into its vector moving the Varma form and to find the matrices AL and BL. So in essence, question 3A part 2 is asking you to put the model into its Varma representation and was asking you to find what the AL and the BL matrices are, polynomial and so on. Then part B then was about Cholesky decompositions. Okay, so we got inflation, growth rate, and output gap and inflation, and it was asking you about impulse response functions and the Cholesky decomposition. Okay, and then question 4 was then about unit root models. So it asked you to derive the mean and the variance of a random walk model. Then it asked you to derive the impulse response functions for some time series processes. And then finally there was a question about unit root testing. So we'll cover these 2 first, have a quick break, and then we'll do question 2 from the previous year. Okay, so question 3A then from part of last year. If everyone's got the questions, we've got a model in equation 7, we've got a VAR1, and we're given the phi1 matrix. So we're given in the question that we're told that phi1 is equal to. So again, if you got we're going through the solutions here, but if you've got the question with you, so you can see all the. This is the phi1 matrix, and it asks us to verify whether or not yt is a stationary process, being sure to show all relevant mathematical working developed in your answer. So here we can use the characteristic function approach. So again, remember, in order to show stationarity, we have to have that we first derive this characteristic equation matrix here, and then we've got to show that we derive the determinant of this matrix. So we work out the determinant of this matrix here, this characteristic equation, and it will be some polynomial in lambda. And we have to then show that the roots of this equation are both less than 1 in absolute value. So again, all you have to do here is state what the characteristic equation is, and then state what the conditions are. So you work out the characteristic equation, and again we went through in lectures why this works, this method works. Remember, the reason why it works is, and we'll see this on the next part, is when you put the model into its Varma representation, we can decompose the vector autoregression into 2 parts. The left-hand side will include all the AR components, and we have to have that these polynomial factors with roots less than 1. So we covered this in the lecture, but again, we saw 2 ways of doing it, and this is one way. So again, state the characteristic equation, you work this matrix out here, we then work out the determinant, and again, the determinant of a matrix is just, again, call this A, B, C, and D. It's just A times D minus B times c. Okay, so this is a formula for the determinant. And again, this is just a quadratic in lambda. And then we factor this out. So again, we can factor it as such. Again, to work this out, you could use the quadratic, you can use the quadratic root formula. But again, you're just factoring a quadratic. So we can see then that this characteristic equation minus I1, it equals naught when lambda equals 0.5 and lambda equals 0.6. And again, both of these are less than 1 in absolute value. Okay, so the key part then is to just state the characteristic equation, work out its determinant, and then note that a process is stationary and both of the roots are less than 1 in absolute value, and to make that clear, and then to show that this is the case for this model here. So again, this would then get you all the marks for this question here. Okay. So part 2 then was asking you, in essence, to put the model into its Varma representation. So we know how to do this. So this goes through the method, but we know broadly if we have that yt equals, and again there's no constant here, phi1. So again, we went through why this works in the lecture. Then we can rewrite this equivalently as yt equals L yt. Sorry, time go away. Equals phi1 L plus epsilon t. So again, we can then put it into its lag operator form. So again, we can rewrite it equivalently, and then again. Yt equals epsilon t. Then we multiply both sides by the inverse of this matrix. And again, but we can note that, so we want to multiply both sides by the inverse. So call this phi L. This is what this matrix is here. This works this matrix out for this particular question. So we have phi L equals phi L yt equals epsilon t. Okay, and we know that the inverse of a matrix we can rewrite as the adjoint of phi L divided by the determinant of phi L. Okay, so we have that yt, we multiply both sides by the inverse, is equal to the adjoint. Again, multiply both sides by the inverse, so we're plugging this in now to here, is the adjoint phi L divided by the determinant of phi L times epsilon t. Multiply both, again, L behaves like a polynomial, so we can multiply both sides by the inverse of this and plug in this general expression here. And then you can multiply back over here. So we can then get we've now got the Varma representation. So this is the general formula when there's no constant. Equals the adjoint of phi times epsilon t. Okay, so this is just a quick recap as to what the Varma is. And this is, again, relates to the stationarity. So again, we've now re-expressed this simple AR1, we've now re-expressed this model equivalently as this one here. So this is the Varma representation when there's no constant. And again, this is just a general method. So in this particular example, all we have to do is state this. And again, the question just asks you what are AL and BL. It doesn't say to formally derive them. So you could, if you wanted to, just state the Varma representation and then work out both of these entities as we've done here. I've just gone through this just to recap where the Varma comes from. And one of the main benefits of the Varma representation is that it decomposes the model into the left-hand side. We have the AR component, which is crucial for stationarity, and relates to why doing this characteristic equation method works. And on the right hand side we have all the MA components on the right. So this is why it's useful. Again, this wasn't related to the question, but remember, just to recap, the reason why this is useful and the reason why we often work with this is because we now know in order for the process to be stationary, we have to show that the roots of, this will be a polynomial in L, we have to show that the roots of this polynomial are less than 1 in absolute value. And again, you could have done this for the answer above, for part 1. For part 1, we use this characteristic equation approach, but equivalently, you could just note that we have to show that the roots of this polynomial have to be less than 1 in absolute value. Again, they're both doing the equivalent thing. I think it's more intuitive to remember it this way, i.e., once you put it into this form, we know that everything on the right-hand side is always stationary, so we just have to determine that the left-hand side is stationary, and the crucial thing is that this polynomial has all roots that are less than 1 in absolute value. Okay, that relates to the first question. So that's it. And again, just to reiterate, because the question didn't ask you to formally derive AL, it didn't ask you to explain why, you could just state the Varma representation and then work out the relevant matrices. So then from then on it's relatively straightforward. So we have, sorry, it's going really slow for some reason. So we have, well, we've got the phi L matrix. Remember, this is just I minus phi 1L, and this, we've got the phi 1 from above. Okay, and that's it. We worked out the determinant above of this matrix. So we work out the determinant with this here, and then we work out the adjoint, which is just this here. So again, that's it. So this question, I think, was relatively straightforward. You firstly just have to note that we have the Varma representation. So again, you note this, and we note this, and then you work them out for both parts. So hopefully you can see then, you can see the answer here as well, so you can write this down. You can see what the final answer is. Okay, so I think these questions, I mean, it looks quite hard, but this question is relatively straightforward. You're just rearranging an equation and using the Varma representation. So again, it's also, in this question, you could have just stated the Varma, but I think it's always useful to understand where it comes from, such that on the day of the exam, if you forget or you're not sure, you can at least convince yourself that this is the correct way of doing it. Okay, so if there's no questions on that, we'll move on to the next part. Okay, so now the next question is 3b. So we have a researcher is interested in understanding the connections between inflation, the output gap, and the short-term interest rate in the UK. To this end, she uses quarterly data over these periods to estimate a reduced form VAR4 for the model, which has 3 variables in it. We've got inflation, then output gap, and then short-term interest rate. Figure 7 in the appendix shows a subset of the orthogonalized impulse response functions calculated from this model. Okay, so the researcher understands that, so part 1. So the researcher understands that the calculation of the orthogonalized impulse response function in this way involves assuming these macroeconomic variables are related via the following structural VAR. Okay, and it gives you the structural VAR in this question, subject to certain parameter restriction. So it asks you to state and interpret these restrictions on the parameters. So this question is about the Cholesky decomposition. So what this says is, again, we have this form here. It's telling us that we have this form gamma naught yt equals alpha plus the way to think about this is you've got the VAR and you can multiply both sides by a matrix like we did in the lecture. We saw that when the errors in the original model are uncorrelated, we can multiply both sides by some matrix. In this case, you can think of it as this gamma naught here, and transform the model such that the new residuals will be uncorrelated. So you can think about taking a VAR like this. The original model could look like this. Call this alpha star. It's a slight difference from the question, and then equals alpha. So the original model would be like this. This is what a reduced form VAR is for a VAR4. Okay, and these errors, these shocks in the original reduced form VAR could be correlated. So we saw that we want to remove this. We can multiply both sides by a matrix such that this will rejig the shock such that they're now uncorrelated. I think we called it C in the lecture, but you can just call it gamma naught. You can think about multiplying both sides by gamma naught. You're going to get gamma naught here and so on. Okay, so there's a slide on this in the lecture. So again, for example, alpha star will equal this. Psi 1 will equal this, and so on. And the new residuals, ut, will be this transform residual here. And we choose this matrix such that it makes all of the new residuals ut uncorrelated with each other. So it asks you then what the restrictions would need to be for the orthogonalized impulse. So you just state the conditions of the Cholesky decomposition. Remember, for the Cholesky, we have that this matrix is lower triangular. So in this case, it would just mean, again, what all this means is that we, for example, like this, all these would be naughts, and these can just be any constants. Call it C. Okay, this would be then a lower triangular matrix, and then we want the ordering to be as in the question. In the question, we've got it ordered as yt equals inf t og t and rt. So this would be odd. So then again, so we just state so that inf is not affected by these two. So this variable isn't affected by this or this. And then finally, then this is not affected by this. So again, we can't have this. This is ruled out, and we can't have this either. So we can't have this or this. So this is what this just says here. We have that in this particular case, we'd have to have for the Cholesky decomposition that inflation is not affected by. So inflation could affect the output gap and interest rates, but not the reverse. And then finally, then that the output gap could impact interest rates, but not the reverse. So again, we've got this here. So in essence, this question is just asking you to state what the conditions are for the Cholesky decomposition. I've just given you a bit more detail as to where this model comes from. It's kind of phrased in a slightly different way to how we saw it in the lecture, but technically, when we do the Cholesky decomposition, we're taking a var and we're transforming it into something that technically will be a structural var. So remember, for a structural var, it has this matrix multiplied by yt. In this case, we're choosing the gamma naught, this psi naught matrix. So we're selecting it and multiplying both sides through, such that we're not estimating this here. Well, we're fixing it in. Okay, so that's what this question was getting at here, and why it's phrased in this particular way. Okay, so part 2 then is asking you to explain the interpretation of the plot entitled Response of OG to OG. So again, go to figure 7, which gives you the impulse response functions. Okay, and we want the bottom right hand graph. Okay, so what does this graph show? Well, you just literally have to state what the graph is showing us. So you're just expected to state that it shows the path of OGT to changes in a response to a one standard deviation to the transform shock. So again, remember, when we do the Cholesky decomposition, we're now introducing a shock to ut, not epsilon t. Okay, so when we transform this model, we now do a impulse response in this model here. So we would introduce a one standard deviation shock to ut, and that's what this is saying here. So in essence, this ut strips out all correlation with shocks from other variables. Okay, so you just expect to state this question wasn't asking you to state. Was asking you to explain what the graph shows you broadly. It wasn't. You could have done. You wouldn't have lost any marks for adding in that there's a. You could have interpreted the graph and said that there's a positive effect initially and it gradually declines and becomes negative by period 10. But what the question was asking you to show is like, what actually does this graph show you in general? In general, it's showing you what the response to the OG is to a one standard deviation change to the Cholesky factorized innovations, i.e. the UT from this transform regression. Okay, so you'd be expected to write something along the lines of this given here. Okay, so you can get this down for Okay. So the next part then, 3b part 2, sorry, part 3, 3b part 3, briefly summarise what the impulse response functions in figure 7 tell the researcher about the relationship between inflation and the output gap. Okay, so in essence then, you'd be expected to interpret the graphs. So what can we see then? Well, we can see that the shocks to inflation has a positive but seasonal impact on inflation, where we can see that a shock affects the inflation t and t plus 4 and t plus 8. Okay, so you can see this from the impulse response function. So in essence, you're just expected to interpret the graph. You're expected to interpret the response of inflation. So if you go to the graph, we can see that there's a spike at period 4 and at period 8. So remember, 1 in the graph, lag 1 is the contemporaneous interest rate. So what about the effect of inflation on output gap? Well, we can see then, when we look at this, if you look at the graph, remember the standard error band give us, the red dotted lines give us a 95% confidence region for that particular response. So if naught belongs in this confidence region, that means if we do a test at that lag, we can accept the null hypothesis at the 95% significance level that there's no impulse response at that particular shock. And we can see that it's insignificant. We can see that the response of OG to in, so this is the third graph in the bottom left, we can see that there's, if we'd accept the null at all lags 2 to 10, all the dynamic lags, we can see that all of these would accept the null hypothesis that there's no effect. So you'd be expected to say this here. Okay, and again, so you just need to interpret all the graphs. So we can also see then that we can also see, sorry, so this, just to be clear, these should be used here. The shocks to the transform. These are all Cholesky these are all the Cholesky shocks. Okay, we can see then that by construction, the Cholesky shock to output gap has no contemporaneous effect on inf, but it has a positive effect one period ahead, and then is insignificant for all periods after that. So again, remember that when we ordered by the Cholesky ordering, we ordered it such that OG couldn't impact inflation. Remember, we ordered inflation first and then the output gap. So again, you'd be expected to note this. We can see then that period 1, remember period 1 is the contemporaneous effect. We can see this is always not by construction, and we can see that then there's only a significant positive impact at lag 1, which is 2 in the graph, and then it's insignificant at all further lags. Namely, when it says insignificant, you'd be expected to state that we would find evidence to accept the null at the 5% level that there is no response at lags 2 onwards. Okay. So again, you'd be expected to give a little bit more detail. These are just very broad. These are the key points that you should mention. But again, you'd be expected to give like a little bit more detail in this in your answer. Finally then, we can see that the shock to the growth rate has a positive significant impact on OGT contemporaneously, and then the effect at further lags forward gradually decreases as the time period goes ahead, and it becomes insignificant by lag 5. Namely, from lag 5 onwards, we accept the null hypothesis that there's no response of a shock to output gap now 5 periods ahead and onwards. So again, if you look at the graph, remember lag 5 would be 6 in the graph, and we can see that we'd accept the null there, that there was no effect, and that's the same for 7, 8, 9, 10, which correspond to 6, 7, 8, and 9 lags. Okay, so again, just to recap, all we've done is interpret all 4 of the graphs. So that's what this question was expecting you to do. Okay. So again, if you've got any questions, just type them in the live chat box. Okay, so the last part there was asking you about changing the ordering to the Cholesky decomposition. So, part 4 says another researcher estimates of R4, but now it changes the ordering. So now it orders it like this. So the question gives you this. It now reverses the ordering. Okay. What would you expect the orthogonalized impulse responses from this model to be? Would you expect them to be the same as those obtained from the model for YT? Justify your answer briefly. Well, no. We know that the ordering is crucial. So now in the previous case, we'd allowed OG. We've now, in the previous case, we had, for example, that the interest rate didn't impact inflation and output gap, and now we're allowing for that. So we've now completely changed the ordering. So no, the ordering of variables is crucial because it determines the relationship between the variables implicitly assumed in the Cholesky decomposition. Okay, so again, you'd be expected to note that this is a crucial feature. And again, you can also write it out when you see for example, we'd have something like this. Not. This could be like C1, C2, C3. In the original case, we had inf, OG, and RT equals ... And now we're changing it. Now we're changing the ordering around. So we can see it completely changes when we reorder it. It completely changes how all the variables impact each other. So in the general case, we can see that it will completely change the impulse response functions. Okay, you can see just by looking at it, you've completely changed the regression formula. So of course, even just at the broadest level, you can see that doing it this way is obviously going to change the analysis. Okay, so you'd be expected to. The key thing to note is that the ordering is crucial here, and to give a little bit of detail as to why. The crucial thing is we've now changed which variables can contemporaneously impact the other one. So of course, you're going to find a very different impulse response output graph, and we saw an example of that in the lectures. Okay, so again, and this relates to the project. Again, the crucial thing is that this comes from outside the model. So again, this is something we assume. Like the ordering of causality is not something you can glean from the data. This is something which normally comes from an economic hypothesis and so on. Okay, so are there any questions on question 3? So we're going to move on now to question 4, which was about unit root processes. Okay, so the first part then is question 4, part A, is relatively textbook type material. Okay, so we have that should be sum I equals 1, 2, t. Okay, so we're told that we have a simple random walk. So this just literally comes straight from the lecture slides, where y naught equals naught and epsilon t is a white noise process. So the crucial thing here then to answer 1 and 2 is we want to back substitute. So again, we want to rewrite this as a function of the last t shots. And we saw in the lectures that you can keep recursing back t minus 1 times, and you can rewrite this as yt equals alpha t plus sum I equals 1 to t of epsilon I. Okay, so we've done this in the lecture. Again, go back to the lecture notes. We did this. If you just keep recursing back, substitute yt minus 1 in, and then do that all the way back to y naught. When you do this t minus 1 time, we're going to add alpha t minus 1, which will give us this, and we're going to add all the t minus 1 shots before this down to period 1. So again, this is just literally basic algebra, and we're using this restriction that y naught equals naught. So that's the key part then. So once you've back substituted, well, you just take expectations on both sides to get the mean is equal to this. And again, by the additivity property, you don't need to state additivity, but you'd have to, of course, make it clear that this then simplifies down to alpha t. And again, this is constant, so this comes out like this. Plus, again, we use the additivity property here. The expectation of the sum is the sum of all the expectations. And then finally, then we use you could have stated this in your answer. Again, remember one of the key points of this from white noise, call it say WN1, we have that E of epsilon I equals naught for all time periods here. Okay, and again, so this just equals alpha t. Okay, but again, this is relatively textbook type material. So the key part is to back substitute, and again, we're seeing a common theme here. When we're working out properties of these AR type models, we're always back substituting again and again and again and putting it into its kind of MA type form, as we've done here. Okay, so that was relatively straightforward, I think, that question. And then next part then was to show that the variance of yt is equal to t times sigma squared. Okay, so this goes through then all the derivation, and again, you'd be expected to make all this clear in your answers. So we've got, well, this is the formal definition. We plug in the mean from part 1. So again, you make that clear where this comes from. So we've used the fact E of yt equals alpha t. Okay, well, the next part then follows again from part 1. Yt minus alpha t. We'll just use the formula above. We just subtract, we get this. So that we get from here to here. And then we now square the sum of t terms. So again, we now get the double sum. So again, you can, this is giving you the full, this is going through the full derivation here. So remember, if we have the sum of xt from say t equal 1 to t squared, well, we get the sum t equal 1 to t xt times by the sum. Again, just call it s equal 1, just to change the... Yeah. Again, these are indices. This here, it doesn't matter, the labeling doesn't matter. This here is just shorthand for all the x's added together. This is also shorthand for all of the x's added together. You just denoting the fact they're both, and then that's it. So then we have sum of t equals 1 to t s. This is a general formula here. We've got xt times xs. Okay, this is a full expansion. So again, this here, again, it's just convention. We can just now, we could put the t here again, but again, we're just, these both, this is just the sum of all the tx's times the sum of all the tx's, which is just the sum of all the tx's squared. Okay, so we've used the formula for the double sum here. Okay, and then that's it. We use additivity, gets us down to the next line, and then we use all of the white noise assumptions. So again, because epsilon I is white noise, then all of the cross product terms are equal to naught. So we're just left with all the cases when I equals j. So this is just what's left. This is just when I equals j, we get E of EI squared here. And then finally then you'd be expected to state that this follows by the white noise assumption, i.e. they're all sigma squared. And again, so we've got sigma squared I together t times. Okay, this is a full derivation then of the, you could have gone the other route and used a variance formula and said the variance of the sum is the sum of all the variances because of the white noise and so on. But this is just the actual formal full derivation of the result. What's going on here is that this here gives us the variance of the sum is the sum of all the variances plus the sum of all the covariances, and all the covariances are not here. So this just formally writes this out here. Okay, so again, I think that was relatively straightforward. So these types of questions I think are relatively straight. So again, it's just practice going over these, and also, of course, for the AR1 and the ARMA1 and so on. Okay, so again, the next part then also relates to the so this, we saw this in the lecture series. So again, that's just a type. This is just alpha here. Okay, so the question then asked us, we've given this zt. Where's that come from? Okay, we're given zt, we're given xt, and we're given the, all we've done here is plugged in ut. This is just ut from the question. question. Okay, so we've got this particular AR1 regression here. Okay, and we've got two things here. ZT we can see is a random walk where the errors are in MA1, and we can see XT is just a simple linear trend model with MA1 errors. Okay, so the question part 1 and 2 is asking to derive the impulse response functions of Z and then X. Well, the definition of the impulse response function is just this. It's just dz of. It's told you what it is. So in essence, all you've got to do is work this out. The whole question is about working this out. So we have the model here. Well, you just we need to go forward S periods. So again, we want to work out Z T plus S. So again, this is equal to alpha plus Z T plus S minus 1 plus epsilon S. Sorry, T plus S plus phi epsilon T plus S minus 1. And again, I mean, you can go through this. You should go through this yourselves. If you now go so keep recursing back. So substitute in ZT plus S minus 1 and keep doing this and do this S minus 1 times and keep going back until you get back to having ZT minus 1 here, which is what we've done here. So it's very simple. It's very similar to the above. In the above, we didn't have this phi term here. In the above, think of the question 4a. This is exactly the same form for y, where phi is equal to naught. So we didn't get this extra term here in the above. But we can do this, just keep back, and then can plug all this in. So we can plug this in from, this has kept it, what this has done is kept it all in, these are the UTs here. So what this has done it like this. So we can just use the general expansion from above now for S periods ahead. Okay, so again, think of the answer from above. It's exactly the same here, so we can use this back substitution result here. The only difference is just shift your S periods ahead. Now for S periods ahead, we're going to get S here and go forward S periods. So it's exactly the same method as to how. Go down. Okay, so do this yourselves. We can get this from the above, keeping for now to begin with, keep this just as UT and then plug in all the UTs. So this is UT minus 1, this is UT and so on, and then plug in all of the plug in the UT equals epsilon T plus phi epsilon T minus 1 into here. Okay, and we get the next line. So then this is it. This is the key part. So this is just algebra. So again, go through this yourselves. You should be able to work this out by back substitute. So again, write down the answer, and as practice, if you can't see this now, keep going through it and go back. And if you can't do it, then come to an office hour or email me. But you should be able, or ask somebody else, you should be able to, by simple algebra, get down to here just by plugging in UT from here into there. Well, this is it. So now we've got to differentiate this with respect to epsilon T for all the S's. Well, we can see when S equals 1, then we just get 1. And when S is greater than naught, we're going to get 1 plus phi. And we can see that here, look. We can see that when S equals naught, well, this is just epsilon T here, right? So that would be, when we have different S's, all we've got to do is work out where is epsilon T for different S. So if S equals naught, well, epsilon T just here. And when we differentiate this side, when we differentiate both sides with respect to epsilon T, we're going to get a 1 at S equal naught. And all the other legs, S equals 1 onwards, we can see then that when we differentiate, we're going to get 1 plus phi for all the remaining S. And that's it. Okay? So the key part here was then just to back substitute and to write Z, T plus S as a function of all the past shocks of epsilon T, and then just differentiate both sides for different S's. Okay, so we did this in the, we saw this in the lecture, in the final lecture. We saw it at the end of lecture 7 and also at the start of lecture 8. it's even easier for part 2. We have this form here, and we want to differentiate now with respect to epsilon t. Well, it's simple. We can see for s equals 1. So again, if we can work out xt plus s, it's very simple. We're going to get alpha plus beta t plus s plus epsilon t plus s. Again, this holds for any t, so it holds it t plus s. Well, at s equals 1, again, at s equals 0, sorry, epsilon t is just here, so we're going to get this. At s equals 1, well, this will be epsilon t then. When we differentiate both sides, we're going to get phi. And at all other s, well, there's just not, because at s equals 2, there is no epsilon t in this equation here. So when we differentiate, we're going to get a 0. Okay? So we should also add in this question here, again, this is only for s going back to t minus 1. We can also see here that this will be not for s greater than t minus 1. For the simple fact, when we go back that far, epsilon t then no longer appears. When we go this far back, there will no longer be an epsilon t appearing in here. Just as was the case in this one here, we can see when we go forward far enough, at s equal 2, for example, we can see that we're going to be, let's take s equal 2, then we're going to have x t plus 2 equals alpha plus beta t plus 2 plus epsilon t plus 2 plus phi epsilon t plus 1. We can see that at s equals 2, xt plus 2 is not a function of epsilon t. So when we differentiate, we're going to get a 0. Okay? And we can do the exact same thing for the above. We can see that when we go forward far enough, xt plus s is no longer a function of epsilon t. So again, just to be clear, we'd need this in your answer as well for this type of question. Okay, so I hope everyone's got that down. Okay. So the next part then. Two popular models for a macroeconomic time series are the different stationary or unit root model and the trend stationary model. Contrast the implication of these two models for a macroeconomic time series. Well, different stationary, we'll just take, this would be refer to this model here. Take the random walk model. We can see then that when we difference, i.e. when we subtract yt minus 1 from both sides, change in yt is just alpha plus vt. So we can see what this different stationary literally means. When you take the difference, it now becomes a stationary process because Vt is a stationary process. Okay. Well, we know for this model then, we've already derived in this case that the mean of this will have a potentially linear time trend when alpha is not equal to 0. And we know that the variant will have infinite variance and shocks have a permanent effect. Okay. So this, in essence, you're just reiterating what we found above. We saw this from the impulse-response functions, is that as t gets bigger, as t goes on, there's a permanent, the effect of a, think of this as a shock, the effect of a small change to the shock at time t. How does that impact the series s periods ahead? Well, as t goes on, we can see there's a permanent effect, it never dies away. As t goes off to infinity, the effect of a shock will carry on forever. Okay, it'll be 1 plus phi. We also saw that a different stationary model has variance which is converging to infinity, and the mean of the model is at alpha t. So again, we can have that there will be a linear time trend. Okay, so there, you, in essence here, just had to reiterate what we'd already found above in the question. We'd already found all the properties of a trend stationary model above. A different stationary, sorry. So a trend stationary is just that it's stationary around a trend. So for example, if you take this model, yt itself is obviously not stationary because the mean is increasing over time, or it can increase over time. Okay. what this means is that the shocks around this mean are stationary. We can see in this case, this model also has a mean of the same form as, a similar form as the different stationary. It'll also have a time trend, a possible linear time trend. But the difference is that there's not infinite variance and shocks die away. Okay, so in this particular model, we can show the variance of this the variance of yt will just equal to the variance of vt. Okay, and again we've worked this out because for any t this alpha plus bt is fixed. It will not change the variance for any time period. This will always be equal to each other. This will equal sigma squared. So we can see that the variance around this time trend is fixed, whereas in this case here the variance isn't. We saw here the variance in this model is converging to infinity. Another property is that the effect of shocks at some time period only persist for a finite number of periods. We can see that after here they die away. Okay, so the key difference is that in a trend stationary model, it still allows the linear time trend. The key difference to a different stationary is that the variance is finite and the effective shocks die away at some finite time period. Okay, they're the key differences between the two models. So you would have used your answer from part 1 and 2 and part A here to add to your answer. Okay, so next question then. So figure 8 plots the logarithm of quarterly GDP in the UK for this period. On the base of this plot, a researcher wishes to test the series contains a unit root. Therefore, he runs 3 different versions of the augmented Dickey-Fuller test. Part of the EV's output from these tests is presented in figure 9 to 11. So which version of the ADF test should the researcher use? Briefly justify your choice. Well, we look at the graph of log GDP, and we can see from the graph, if you look at figure 7, it looks like the mean is growing over time. So we would want to allow there could be a constant, there could be a shift and a time trend. So we'd want to use the model which allows alpha plus bt. So remember, for the Dickey-Fuller regression looks like this: delta y t minus 1 plus, and we got the sum of whatever s equals 1 to say however many you want of phi s of the change in yt minus f. Yeah. So again, the Dickey-Fuller, the augmented Dickey-Fuller augments it by allowing you to control for past changes in y, which allows, remember, this would be testing for a unit root in a general ARK model. The key point is that for any regression, the critical values of the Dickey-Fuller test, testing that delta equals naught, depend upon whether we include a constant and or a time trend. In this case, we wouldn't want to set alpha or beta equal to naught, because it looks like the graph of GDP has a shift and a linear time trend in the mean. So remember, the key point here is that there's 2 ways you could have a linear time trend. It could be that yt is just a random walk. In this case, there's no explicit t for a time trend. You don't have alpha plus bt in the formula for a random walk, but we can still show that the mean of random walk will be a linear time trend. Or there could be just no unit root and just yt just is a time trend plus a shock, and they would both give a broadly similar looking graph. They would both increase over time in a similar way. So we need to allow for this when we want to test. If we want to test for a unit root, we have to allow, under the alternative hypothesis, if there isn't a unit root, then it has to be the case that there's at least a linear time trend model going on here. Okay, so again, you just need to interpret the graph and justify which augmented Dickey-Fuller test we would use. And in this case, we would use the figure 11. We would want to use figure 11 gives us constant and a time trend. Okay, so this is under the it says exogenous, and it says then constant and a linear trend. So you need to be able to read these tables and understand what they mean. Okay, this just means it allows this here. It doesn't set alpha and beta to not. Okay, so that would be the answer to part 1. You're justifying which Dickey-Fuller regression that you're going to use to perform the test. The next part then, 4C part 2, asks you then, whatever, given the choice you've made in part 1, in our case we're going to use figure 11, explain what is the regression that's being estimated, what is the ADF test statistic, what are the null alternate hypotheses, and what is the outcome of the test. Well, this is the regression that we run. Again, it called it VT, but again, you call it Y, whatever else. This is just regressing the change in VT on a constant and a time trend plus, call it rho, VT minus 1. And it just controls for one change. It's plus phi 1 change in VT minus 1 plus error. Okay, and if you look at the ADF figures, it says that it includes one lag. So we know it's an augmented Dickey-Fuller regression controlling for one lag. It sets k equal to 1. Okay, so this is the regression that is used to perform the test. So you'd be expected to state this. Well, the ADF test statistic, remember, the null hypothesis is that rho equals 0 against the alternative that rho is less than 0. And again, because we've allowed for alpha plus bt, under the alternative where there's no unit root, it will still have a time trend. It'll be a trend stationary model. Under the null, there's a unit root. Under the alternative, it's just a trend stationary model. And again, so all you'd say here is you run OLS and you form the T statistic. So the T statistic is the OLS estimator rho hat divided by the standard error. So again, it's just a T statistic from this regression here. So you'd be expected to state that. You run this regression and then you form the T statistic as such. This is the null and this is the alternative. And again, we showed why this tests for a unit root. All you're doing is subtracting yt from both sides. Instead of testing that rho equals 1, it's equivalent to testing rho equal 0 here. So we saw this in the lecture, why doing this simple transformation tests for a unit root. Well then, what is the outcome of the test? Well, it's just a t-test, but now the crucial thing is to note that remember, when they're under the alternative, the t statistic no longer has a normal distribution. So you'd be expected to state that in your answer. You reject if the test statistic is less than the critical value, and again, from the Dickey-Fuller distribution. And again, remember, the distribution varies depending upon whether you include a constant and or a time trend. So you'd want the Dickey-Fuller distribution from the third set, which allows for a constant and a time trend. And then you just do this test. So again, you can see that you just go down, if you look in figure 11, which gives you the augmented Dickey-Fuller test with a constant and a time trend. We can see then it gives you the critical values anyway, but we can just look straight at the p-value. The p-value is 0.48, so we can see that we're going to find evidence to accept the null at any conventional significance level. Again, you could do a 10% test or a 5% test. We've got p. We've got the p-value is greater than 0.1. So again, we're going to find evidence to accept the null at all conventional significant levels. By conventional, I mean I've never seen anyone do a test other than 10, 5, 1, or sometimes 0.1%. So again, we would evidence we've got the p-value 0.48 is bigger. So again, be careful to state we never accept or reject a null. We just find evidence to suggest that there's a high probability that the null is true here. Okay. So the next part then was more technical, and again, a lot of this is just bookwork. So for question 4 here, there's a bit of interpretation. You had to kind of give answers and think a little. For question 2, it is more bookwork, but you've seen these, we've gone through these in the exercise questions. So again, we'll just get, if you get the 2015-16 paper now, and we're going to go through question 2. So again, if you've got any questions, just put them in the box. Okay, so question 2 then was asking you in essence to derive the autocorrelation functions for 2 different processes. There were some other bits as well, but this was a crucial part to. Where's the exam gone? Okay. So question 2 from 2015. Part A asks you to provide a formal definition of a univariate stationary process. So again, it's just bookwork. And again, this would be for all time periods. So again, for all of these, you'd state it holds for all. And it's crucial to note this. So for example, if you just wrote it like this as it's written in the PDF, you would lose a mark for each. You'd need to state that it holds, or, well, as long as you state it's constant, or you can write it like this as well. So a very common way people lose marks in the exam on these types of questions is just to write this and nothing else. This here doesn't say the crucial part of the definition of stationarity is that it's the same for every time period. So this is the most crucial bit, is to state that it's constant. So you can write constant, or you can write it like this. Again, we've got that the variance of yt is equal to some finite constant, and finally then the covariance function for any k is just a function of the gap between the two. So again, gamma is just any arbitrary function. It just says this covariance function doesn't depend upon time, and this is a formal way of writing it here. Okay, and you get then 6 marks for this. Okay. Part B then asks you to define the autocorrelation function and for a stationary process and briefly explain its use. Well, we have the definition here. And again, the key thing to note, remember, the formula for the correlation, the general formula for the correlation is the covariance of x and y divided by the square root of each of the. It simplifies here because it's stationarity, the variance of y, t, and the variance of yt minus k are both equal, so we're going to get the square root of the square of the variance of yt. So this here is only the formula for the correlation when it's stationary. So that's a key thing to note here. And that's it. And again, remember, the correlation function is defined for all lags, k equal 0 back forever. So when you're asked to find the correlation function, you find it for all lags, k equal 0 and then back forever. Okay, so it's a function of the gap. Why is it useful? Well, it's useful because it encapsulates the key dependent properties of a process, and it aids in allowing us to try and determine what kind of process the true process may look like. So for example, you could give an example here also. You don't need a short answer here. You could have given an example, but broadly it's that we can use it because it gives us key information on the dependent structure of a process, which can highlight what kind of armor type model it comes from. It may help us to discern between an MA and an AR type model and so on. And that'll be more than sufficient for an answer here. Okay? Okay, so part C then was most of the marks for this answer. And again, it's quite long-winded, but with these types of questions, it's things that you've kind of seen a lot before. So there's a lot of steps here, but it's kind of bookwork type answers. We've got an armor 1-2 model, and you're told that phi1 is less than 1 in absolute value, and it asks you to derive the autocorrelation function of this model for 2 different cases of parameter restrictions. The first one sets phi1 equal to 0. So again, these answers just come straight from I think it was exercise 2. These are just lifted straight from the solutions to one of the exercises. So again, you've already got this here, but again, So there's not really much point. The first one is relatively straightforward. So there's no point me going through this. For when phi1 equals naught, then yt is just a ma2 process. Okay, so I'm not going to go through it. We've done this before, and you've got the answers in your notes, and you can also see it here. Again, crucially, you'd be expected to go through all of the steps. So again, with these questions, they're kind of easier in some way, in that you've kind of seen it before, but you are expected to get a very detailed answer and to go through all of the steps. Okay, so you've got the general formula, you plug in the mean from above, you expand it all out, you use the white noise assumptions, and so on. Okay, and remember, what we're doing here is first working out the covariance function. Remember, the variance is just the covariance at naught. And again, work out at lag 1 and at lag 2. Remember, for an MA2, there can only be correlations at lag 1 and 2. And then note finally then, for lag greater than 2, all the rest are not, because there's no concurrent shocks in either period. Okay, so you'd be expected to note this. And then that's it. So we then have the covariance function of an MA2 model. And then once we've got this, you just divide by the variance. So if we divide both sides by the variance, which is just gamma naught, then we get this here. Okay, you can write it in this succinct form here, or you could just write it. We get obviously gamma naught equals 1, gamma 1 equals da-da-da, gamma 2 equals da-da-da, and then gamma j equals naught for j greater than 2. Again, you can write it like this if you want. This just succinctly writes it in a one form. Technically, actually, I mean, you didn't need to derive the variance here because, of course, you didn't need to do this part here. So you didn't need to do this because, of course, the correlation function at lag naught is just 1. Yeah, at lag rho naught is just gamma naught over gamma naught, which equals 1. Okay, the rho 1 is gamma 1. Oh, we obviously did need to derive it, sorry, because of course we've got to derive it, like we did need to derive it. Okay, so we work out the covariance function, then to get the correlation function we just divide by, so of course we do need to derive the variance. Okay, so you've seen this before. The next part though is a bit more interesting, and again this is also given in this is also done in the video exercise 2. We have now an ARMOR 1-2 model where we set phi1 equal to minus theta 1 and theta 2 equal to naught. Okay, so all this firstly does is just takes a general model given to you in the exam and evaluates it at the parameter restrictions. So we can see that yt has got this form here. Well, as always, you keep back substituting. So you work out yt minus 1 and plug it in, and then go back j periods, and we're going to get down to this here. As always, we get this geometric progression arising in the constant. And when we go back, we can see then that they keep cancelling out, right? So when we go back, you can see a pattern forming. We've done it once, and if we did it like 3 and so on, we can see the general pattern. So again, to do j equals 3 and j equals 4, you see a general pattern that starts to emerge, and it looks like this here. But what can we see then? Well, in this case, when because phi1, it's crucial to state this, is less than 1, well, phi1 j plus 1 tends towards naught as j goes off to infinity. All that means then is that this term drops out. So as we go back forever, we can see that it equals this here. So in this particular case, we can see that this particular ARMOR model with these restrictions is actually just a white noise. It's just a constant with a white noise shock. Well, that's then very easy to work out. It's the correlation function is then simple. In this case, all the correlation, obviously rho naught always equals 1. Well, rho of j equals naught for j greater than 1, i.e. all the correlations are not. The correlations of yt and yt minus j equals naught. It just says this here for j greater than 1. Because remember, epsilon t is white noise, and this is just a constant. So yt is not correlated with any other y, because, of course, yt doesn't depend upon any of the other shocks. Okay, so again, this has gone through in the video exercise, but it's just, and again, this is actually short, although it's worth more marks, it's actually a much shorter description than the before, because it does take a little bit of intuition and thinking as to how you get to the answer here. Okay. So this is, again, we've done this in video exercise 2. All you're doing is recursing the formula once, twice, do it however many times you see the pattern that emerges, write the general recursion for any j recursions, and then just go back forever, and you can, each line is equivalent to the previous one. So you're just rewriting the equation, and then you can just state then. Don't forget to state the final, you got down to the crucial bit, don't forget then to answer the question and to write down what the correlation function is here. Okay. So the next question then, after you define the lag operator, well, this is it for all t, any t. What's a benefit of this? Well, as I've said probably many times in the lecture, the key benefit or key property of the lag operator is that it behaves like a polynomial. And again, it would be the safest way is to give an example here, something like this. Okay, so again, and what it behaves like a polynomial. Namely, I think the key way to get them out would be to give an example here, or to explain it in words. Namely, is that when we do some operation as a function of L to some process, any equivalent polynomial transformation of that retains the they remain the, so namely, for example, you could just say that 1 minus L squared of yt is equal, 1 plus is the same as 1 plus L. Okay, so you could just give an example. If you're not sure you can explain it clearly in words, it's just give a simple example as to what you mean by the fact that we multiply both sides by some operations in L, that any equivalent polynomial expression for that operation retains the same properties when you apply it to a variable, which is what we've shown here. Okay, and the next part then asks you to then, in essence, just use this property. So for then, this next question is suppose that the shocks from the armor model in part C follow a simple AR1 where VT is a white noise shock. It asks you to then, so in essence we've got this, just to rejig what the question tells you. Again, so it's saying the shock in this model, and again I think this was also in an exercise 2. Okay, all it's asking you in essence is to rewrite the equation from 4 now as a function just as the shocks v and past values of y. So, as always, write epsilon in its lag operator form, multiply both sides by the inverse of this using the property that it behaves like a polynomial, and then plug this back into here. And go through. Okay, so we've seen this should be, yeah. So all you've done, put this in its lag operator form as well. This is 1 plus phi1L plus phi2L squared epsilon t. Okay, so you can rewrite like this, and then plug epsilon t in here. That's all that we've done here. Is put this part into its lag operator form, and then plugged in epsilon t into here, and we get down to this line here. So this is epsilon t, yeah, and then multiply, and then plugged in to here, and then we'll just expand it all out. So then you multiply both sides by 1 minus beta 1L, and then that's it. We've now got a quadratic, again, we can set L equal to 1 here because the lag of mu just equals mu. On the left hand side, we've got a quadratic polynomial in L, and on the right hand side we've got this here. So all you do is expand out the left hand side, we're going to get a quadratic, and then take it to the right, and we get this. This is actually very related to one of the questions in exercise 2. So it's literally just algebra. The key part is to write epsilon t now as a function of vt and plug it back into the original equation, and then to expand it all out. So from there on in, it's just algebra. So then you just write. Then we can see then that we can write now. This is the constant. These are the coefficients on yt minus 1, yt minus 2, and on the shocks. So that's it. Okay, so that's everything then. Question 2, I think, again, it was much more standard, but again, it's key that you get all the steps correct. Whereas some of the other questions, 3 and 4, where you had to kind of think a little bit. But that's it. So hopefully that was helpful. And so that's it. So I guess good luck to everybody on the exam next week. And again, this will go on my YouTube channel now, if you want to watch any of it again, to take any notes later. Okay, so right.